degree I did my undergrad degree at Harvard, and this is the first time I'm giving a talk at Harvard in my professional life. So this is a delight, especially. And I only wish it was in person, but what can we do? So this work is was done in, or is being done in collaboration with one of my students, Shuai Sirui, or Sirui Shuai, depending on how you read it. And because we have a very broad set of people watching this talk, I hear there are a lot of mathematicians and just like non-physicists in the audience. So I'm going to have to start very slow and general. And the technicality will, the level of technical innovation is going to increase further down the talk. So in broadest terms, this talk is about the ADS-CFT correspondence. This is a famous and exciting duality between one theory in physics which does contain gravity and another theory in physics which does not contain gravity. So the gravitational theory, it could be lots of choices of a gravity theory, but suffice it to say that it is some quantum theory of gravity with fixed boundary conditions, which are asymptotically ADS boundary conditions. And asymptotically ADS just means some specific falloff of all fields that define gravity is being assumed as you go to infinity. So that's one side of the duality, some complete theory of gravity with specific boundary conditions. And on the other hand, we have a theory, which is a conformal field theory. And the point about that is that it is a theory that we know and understand very well. And in principle, we can calculate anything in it. And so this duality, which is now more than 25 years old, or 25 years old, and lots and lots of papers have been written about it, it is remarkable because gravity in general is, we don't know how to quantize it, or there are a lot of attempts, but there is no definite way of defining a quantum theory of gravity. And here we have a definite example where we do have a theory of gravity, which is in principle complete, and we can formulate in principle any question in it in terms of a language that we all already understand very well, which is the language of the conformal field theory. And so the way that we can use this duality is if we know the dictionary between the two sides of this picture, then you want to learn something about gravity, you reformulate it as a quantum field theory question, and then using the translation dictionary, and then you study an ordinary quantum field theory that we already understand. I should say that there are also other ways of using the duality. Some people say we're interested in a strongly coupled critical system, which is described by this conformal field theory. And because it's strongly coupled, therefore I don't exactly know how to do calculations on this side of the duality. I'm going to use gravity to learn something about it, because I can also translate a difficult problem here into some hopefully easier problem here. So this general way of using the duality is sometimes called ADS-CMT for condensed matter theory. I just want to emphasize that this is not what I'm doing. I'm going to be getting lessons from about this side by asking questions on this side. Okay, are there any questions about the overall structure of where we are in this talk? So if there aren't, then I will proceed. So if you ask me what is the most basic lesson at the level of slogans that we have learned about gravity using this duality in the last maybe 15 years, then I would say that we have learned that gravity is really about quantum information in the conformal field theory. So I really want to say that this is a remarkable and not an obvious lesson, but it is the lesson that seems to be emergent from using this duality to do what we said, which is ask questions that are difficult in gravity by reformulating them in the language of this well-understood dual conformal field theory. So it seems that whenever we ask a question of key importance about gravity in ADS, out pops some answer which really, in an essential way, involves quantum information theory on the other side. And so maybe gravity is just about quantum information. And the most famous example, maybe the starting point or like a cornerstone of this general relationship, is what's called the Ryuta-Kayanagi proposal. And so to say what this means, I have to take these two sides of the duality. The vertical direction in these cylinders corresponds to time. And so I'm going to look at an equal time slice in the CFT. And I'm going to assume, this is a subtle assumption, but for the purpose of this talk, it will work, that the CFT can be the Hilbert space of the CFT. So the space of quantum states can be written as a tensor product of an A Hilbert space and an A bar Hilbert space. So A bar is one part of this spatial slice, and A bar is the other part of the spatial slice. Then any pure quantum state in this Hilbert space can be in principle written in this form. You may ask, well, is it really a sum or maybe an integral if I'm in a big infinite dimensional Hilbert space? But again, ignoring that type of subtlety, we basically have this structure of a state. And then you ask, if I'm going to just do experiments on system A without looking at a complement, then it turns out that you can, or a moment start reveals that I can just trace out the system A bar, and this operation of tracing out A bar corresponds to dropping all the information, and out pops this object, which is what's called the reduced density matrix on the state A. So even though the state overall is pure, after forgetting the information about A bar, I will generally get a reduced state, which has roughly this structure, and this is a mixed state in general. Because this is a mixed state, we can now compute the von Neumann entropy of the state. So this is the formula, and this is going to be some number. And the statement is that this number by itself is a measure of quantum entanglement between the state A and the state A bar, between A and A bar in this state. And so this number can only be zero if the quantum state is a product of something in A and something in A bar. But the moment I have what's called quantum entanglement between the two sides, this number is going to be non-zero. So here I described for you how we would compute in quantum mechanics and in this quantum system, which is a conformal field theory, how in principle we will compute a number which tells me about how much entanglement there is between A and A bar. And that's something that we can just do in any quantum mechanical system. But now, in regard to the duality, Ryu and Takayanagi, these two people come along in 2006, and they say, well, how would I compute this quantity in the ADS language? Because remember, we have a duality. So any physical quantity here should have some kind of representation on this side. And their answer is that basically the simplest possible answer, the simplest thing you could imagine, which is the area of a minimal surface, which through the bulk, so through the interior, through this ADS spacetime, which separates A from A bar. And so we have well, that's their answer. So we have a duality between an essentially quantum mechanical quantity on this side of the duality, equaling the most intuitive geometric kind of object or quantity on the other side in ADS, which is the area of a minimal surface. And this is an example of what I meant, that whenever you ask questions about gravity or about the dynamical geometry of spacetime, it seems that you're getting answers that involve quantum information theory on the other side. And this is probably the most basic and the best manifestation or example of this general slogan. So sometimes we say gravity geometrizes boundary entanglement. Any questions about what I said so far? So if there are no questions, but I do encourage questions, especially for this broad audience, then let's talk about the Ryuta-Kayanagi proposal in a little more detail. So here I redrew the picture from the previous slide. And there is a little bit of there's a spatial slice. There's a subsystem of the spatial slice, which we called A. And here is a minimal surface through ADS, which computes the entanglement between this region and the complement. And what I want to draw now is exactly the same picture, but with ignoring time. So just an equal time slice. So here is that picture. Here's an equal time slice of this picture. And here's an equal time slice of the right part of the cylinder. This is the CFT language. This is the ADS gravitational language. And I want to say that, so Ryuta Kainagi told me, if I want to compute the entanglement entropy of this region, I have to find this minimal surface. So I drew it for you here. And there are a few things to emphasize about this. I can't emphasize enough how important it is that we are looking for a minimal surface on this equal time slice. You might say, or people who are familiar with gravity might say, this minimal surface on an equal time slice is not a covariant object. Because why do I have how did I even fix a time slice of this spacetime to begin with? And so the answer is that there is some covariant generalization of this statement, but we will be ignoring the issue of time in this talk. We assume that there is a spatial slice, and in that a favored spatial slice or preferred spatial slice through the bulk of ADS. And under that assumption, we're always looking for the smallest area possible. And this smallest, this minimality, will be something very important in the remainder of the talk. Another one is that, or another thing to remark is that there is a homology condition associated with these minimal surfaces. So in this case, where this spacetime doesn't have any holes or any genus in it, there isn't really a question of what are the admissible minimal surfaces. But you can imagine that in a not simply connected spacetime, there might be a question, well, what kind of topology does this surface have to have? And in that context, the answer is that we're only admitting surfaces in this minimization, which satisfy a homology condition. In other words, take that surface and the original region A through the boundary, and together they have to form the boundary of a higher dimensional manifold, which I marked here in orange. So if you can draw an orange manifold, the region in the boundary which was given in the problem, then you are then that's an admissible surface. So this homology condition will be it will not be very manifest in the talk that it's important, but it's actually important. And then I should also say that there is this area is a classical, so not a quantum construct in gravity, but there is also a quantum extension of this formula, and this quantum extension we will probably use in the last 1 or 2 slides of this talk. But for the moment, it is not important. So the take-home lesson from this slide is remember that we're looking for surfaces, and remember that they must be minimal. The minimality is really the most important thing to remember. Any questions so far? So okay, so I want to apply this Ryuta Kainagi prescription for computing the entanglement entropy in some gravitational spacetime in the ADS-CFT formalism. So I assume that I have a boundary where I can talk about regions such as A, but I want to compute it not for a single connected region A, but for a disjoint region. So a region that has 2 connected components. Let's call them A and B. So the question is, what is the entanglement entropy in the CFT for a region which has the form A union B? And A is connected, B is connected, but AB is obviously disjoint. And roughly speaking, there are 2. So we're looking for a minimal surface which is homologous to the union of these 2 regions. And we have 2 options. One option is I could just solve this problem separately for A and separately for B, and take the union of the corresponding surfaces. So here is the surface which, according to Ryuta Kainagi, computes the entanglement entropy for A. Here is a surface which computes it for B. I'm just going to take the union of these 2 things. This is what I call the green option. And the green option is basically SAB equals SA plus SB, because I made the answer, I got the answer by adding up component answers for the A problem and for the B problem. But there is also another surface, and that other surface would reconnect the endpoints of these intervals, or in a higher dimensional context, it would somehow connect the borders of regions A and B in some non-trivial fashion, so that altogether these surfaces would connect A and B. So this homologous region in the bulk would be connected, and there would be one homologous region which has A and B as parts of its boundary. So this is what I call the pink option, yes. And so generically speaking, I will have at least these two options when I have a disjoint region. But let's remember, I've emphasized the importance of minimality. Let's remember that in the end, Ryuta Kayanagi will tell me to take the smaller of these two options. So this purple option, the one where A and B become connected, can only be activated, it can only apply if it is in fact smaller than the green option. And so I have two possibilities when I compare SAB to SA plus SB. Either SAB is equal to SA plus SB, or that's in the green option, or in the purple option, well, the purple option gets activated if it's actually smaller than SAB. So regardless of which of these two cases is activated, regardless of whether the green or the purple applies, in the end, it will always be true that SAB is bounded from above, but by SA plus SB. Is that logic clear? Where SAB is a minimum of two options, one of which includes SA plus SB. Therefore, whatever it is in the end, it's definitely no larger than SA plus SB. Any questions or comments, and was it clear what I just said? So if no one is raising any questions, then I will proceed. So this statement is evident at the level of surfaces, but it is not evident when we go back to what we're actually computing in terms of in the quantum information theory. Remember, each of these surfaces, according to Ryuta Kayanagi, is representing for me an entanglement entropy of a quantum subsystem. And so you can say, is there any reason why, if I have two separate systems, A and B, the von Neumann entropy for A and von Neumann entropy of B added together, is there any reason why they should be larger than SAB? And the answer is yes. This was proven, this statement, at the level of quantum mechanics, not at the level of surfaces, but for actual entanglement entropies, was proven, I think, in 1970. But it is a highly non-trivial thing to prove. And the proof takes lots of pages and is and involves some very tricky algebra. But
I would say that about strong subadditivity, but you're just saying that just about subadditivity?
Oh, okay. Maybe I should. Oh, okay, you're asking me to say the proof of subadditivity is simple. The proof of strong subadditivity is not.
Yes.
Is that the request?
That's the sign of the complaint. Yes.
Oh, okay. Okay. Then I'm going to let me rephrase. So Daniel, an expert here, is saying the actual thing I'm talking about here maybe is not so hard to prove, but then there is a corresponding or similar statement which is harder to prove, and it will be equally easy to prove at the level of surfaces. So yes, I'm willing to withdraw that specific statement. The specific thing that you should trust me, and I think Daniel will not object, no one really would object, is that there are statements out there about these von Neumann entropies which are difficult to prove, but the proof is always substantial. Maybe some of them are even easy, but the proof is always substantially easy to the point of being trivial when you say it at the level of surfaces. And so these surfaces somehow manifest or geometrize some much more complicated logic in the level of pictures. And the question is, okay, and so we will be, so the idea of this talk and the whole reason for this talk is to use a similar analysis to what we have seen on this slide. So we'll be using manipulations just like what this slide is showing, but there will be more regions to play. There will be, in addition to A and B, there will be some C, D, and E, and so on. And we will arrive at a lot of other statements of this type. And then one question you can ask is, well, are these statements, well, are they easy to prove in, using the definition of von Neumann entropy? The answer is definitely not. We will also find statements that are just not true in quantum mechanics, but they are true here. In other words, there will be some inequalities that of this, which vastly generalize this one, which are true at the level of surfaces, but they are not true for all states in an arbitrary Hilbert space in quantum mechanics. And then we can ask the question why they're not, and we will be doing it later down the line. But the idea for the rest of the talk is to use reasoning such as this one, redrawing these surfaces, maybe cutting them in some ways, arriving at inequalities of this type, always very simple geometric manipulations, and we will try to identify what we can say about such surfaces and why. Yeah, any questions about what will happen next?
Can I ask a question?
Yeah, please do.
Just a clarification about the purple surfaces. So you're trying to compute the entropy of A union B, right?
Yes.
And so there is the obvious green option in which you take the two surfaces homologous to A and homologous to B.
Yeah.
Right. And then the second option you're saying is this big large curve, right? The surface which contains both A and B. And do you subtract the smaller purple surface area from that big area? Is that what you do?
No, you don't subtract them. You just take the smaller option of the two.
Right, but the smaller option, I mean, you would not say is homologous to A union B. Would you do that?
Oh, you would. So the thing is that whatever is sitting between this purple thing and the A and the B, I could color this whole region, and that would be my manifold with boundary, whose boundary is A, B, and the purple thing.
Ah, I see.
Yeah, so it is homologous.
Okay, thank you.
Yeah. Okay, so the objective is so the objective for the remainder of the talk is to use an analysis like this one. There will be some statements which basically tautologies at the level of surfaces, and then we will study. First of all, we'll try to derive as many such statements as possible. We will also try to interpret them, and there will be various layers of interpretation to it, and those layers of interpretation will tell us something quite important about gravity at the end of the day. So that's the goal. Okay, so I think I'll move on. So here is I prepared for you a list of known inequalities of this type, which was known as of November 2021, so 3 months ago, before we put out our paper. And this is a complete list. So so subadditivity, we have just seen it. That's the one from the last slide. There is a statement called monogamy of mutual information, which is this one. So you see there's an A and B and a C in it, and that's the inequality. Then there is a family of inequalities called cyclic inequalities. So they don't have to. So here I gave an example of a cyclic inequality where I have a total of 5 regions, A, B, C, D, E. And hopefully you can see that there is a cyclic symmetry here because I have A, B, C, I have B, C, D, C, D, E. So every term here, oh no, not the term here, but the terms here come in orbits of a cyclic group. And so this is an example of such an inequality, but I can write a similar statement where I have not 5, but 7 or 9, any odd number of regions. So here I have 5, A, B, C, D, E. So this is the cyclic inequality. And then there are 4 what I would call exceptional or complicated inequalities, and I'm going to show them to you right now. Here they are. So it's this one, and this one, and this one, and this one. These 4 at the bottom are the difficult, exceptional, and complicated inequalities that were known before. This is from a paper by Sergio Cuenca, who is now a postdoc at Berkeley from 3 years ago. So
he's now a postdoc at MIT, actually, or will be in the fall.
Oh, sorry. I thought he was. Oh, well, thank you for correcting this. But I thought he was going to Berkeley. Okay, but
well, it's
obviously
news to me
no better.
if it's true. Okay.
So thank you for correcting this. I did give one talk where I made this statement, so I apologize for this. And I guess he's now a grad student at UCSB still, right?
That's correct. Yeah.
Okay. Yeah. Okay. So thank you very much for this rectification. But anyway, so he is the author of these inequalities. And I think it's fair to say that we can have two types of reactions to these inequalities. One is we can be sort of overawed and impressed that, well, that they are true and that we were able, or someone like Sergio was able to find them. On the other hand, I think it's also fair to say that we can feel kind of demotivated by these inequalities, because it's a little difficult to believe that we'll be able to look at, let's say, inequality number 6 and extract some meaningful insight about what this actually means. And so if the purpose was to learn something about gravity, then this inequality is maybe, well, yes, it's just telling us that this task is very difficult, to say the least. And so as a teaser, let me just tell you that at the end of the day, I will be making a statement about kind of about this inequality, which in the end ties very closely to the physics of black holes and specifically to the black hole information paradox. And so if you look at this inequality, I would say it presents a big challenge. And this talk is about reporting progress in tackling this challenge. To some extent, I think the challenge is actually solved. So that's where we are going with this. Any questions about the inequalities and why I'm giving the talk? So maybe while there are no questions, I should say that these other inequalities, each one of them other than the top one, are, I write here that they are necessary conditions for states which have semi-classical bulk duals obeying Ryuta-Kayanagi. So basically what this means is that these are necessary conditions to actually have a space-time to speak of. But, and why do I say this? I say this because unlike this top inequality, these ones are not generally true. And so I was, so Daniel and I had a little back and forth about whether this one is complicated to prove or not. But if you try to prove these ones, you will find that they are just simply not true in full quantum mechanics. In other words, there are always some states in the Hilbert space that violate them. And yet we were able to prove these inequalities, or Sergio was, for at the level of these surfaces. So how do we reconcile these two facts? The fact that on the one hand, these inequalities are expressly violated by some states in the Hilbert space, but on the other hand, these at the level of drawing these diagrams and surfaces, the inequalities are true. And so the answer is that when you take one of these states that violates one of these inequalities, that state has just no hope of realizing a geometry, a classical geometry in the ADS-CFT correspondence. So these states are there, but they just don't represent space-times, or in other words, I would say that they are essentially quantum gravitational states that don't have any classical interpretation in terms of metrics and such. And so by studying these inequalities, we are learning about necessary conditions for a state to have a quantum entanglement of such type that it permits an interpretation as a geometry. So that's why we're studying these inequalities. Questions about that? Okay, so I'll move on. Oh, and here's an example of the kind of state that violates inequalities. So this is called so the inequality we're going to violate with a specific example is the monogamy of mutual information. I just wrote it for you here. And if you take this state, which is called the 4-party GHZ state, it's very easy to see. So this is a state on 4 parties, A, B, C, and some unnamed 4th party. It's easy to see that each one of these entropies is equal to log 2. And we have 3 terms on the left and 4 terms on the right. So the inequality is violated by this. And the kind of comment that would go with this is that this GHZ state can just never represent a semi-classical geometry. Okay.
Bartek,
so yeah.
Can I ask a question? So in this story, you're only doing the leading classical approximation in the bulk, right? So
yeah.
So when you said that, like, how do you know these inequalities? How do you know they hold? I mean, do they always hold with quantum corrections, or like the inequalities you prove using minimal area surfaces, are they modified when you introduce quantum corrections?
The inequalities themselves will not be no, it's that we're proving the inequalities. The inequalities themselves are a given state can either satisfy them or violate them. The point is that we derive those inequalities by assuming the Ryuta-Kayanagi proposal. And so essentially the statement is whenever you have a state that violates an inequality, that means that Ryuta-Kayanagi just doesn't work there. And we would what
I'm saying is Ryuta-Kayanagi technically also doesn't work once you move away from the classical limit, so you have to correct it, right? I'm just asking, when you make those corrections, are you saying all those inequalities are still correct? Like you don't have to worry about the quantum corrections. Like the leading correction would be like the entanglement entropy.
No, for this GHZ state, the inequality is just violated, period. So there's no corrections are going to salvage the inequality, because this is supposed to be a microscopically correct statement of like, you take the state, you compute the entropies, you find a violation. If you computed your entanglement entropies correctly in the boundary, then there is no way that anything that you change or modify in the bulk is going to change the story. So it is a fact of life that states in the CFT Hilbert space exist which violate this inequality, and that violation is not sensitive to how you modify or correct the Ryuta-Kayanagi proposal.
Okay.
Okay, so the goal is to learn about about these inequalities. In particular, we will be interested in states that saturate the inequalities, because states that saturate the inequalities are sort of borderline in the sense that they are barely marginally consistent with the Ryuta-Kayanagi, but marginally so. So a small perturbation of them would remove that consistency, it would render them inconsistent with Ryuta-Kayanagi. So presumably such states are interesting. And so let's try to learn about what they are. And a preview is that, or a spoiler is that we will find that these states correspond to stages of evaporation of black holes. That lots of these inequalities that I will discuss in a moment, they will be saturated one by one, and they will be saturated one by one through states which represent stages of evaporation of black holes. Okay, so we need to have a little bit of a change of strategy here. So because Sergio showed us this remarkably complicated inequalities, it's pretty clear that we will not make much progress just by thinking hard about that specific inequality. And so we need a little bit of a change of strategy, and here it is. Let's focus on average entropies. Average meaning average single region entropy, average double region entropy, and so on. So we'll study S of, okay, so what do we mean by this? Suppose that I have divided my boundary, this conformal field theory, into A, B, C, and the complement. So now we will call this the free region setup. Then I have SA, I have SB, and SC, and each of them is an entropy of a single region. In fact, the complement that I left out, which I would call S of ABC, but is also some remaining fourth region, which I didn't give a name for it, but it also should be treated as a single region. And so, so now we can say, let me take SA and SB and SC and this remaining region SO, its entropy, and then we take the average of them. This average is the kind of thing that we will be studying in this talk. Now, when I have three named regions, the average involves A, B, C, and the complement. When I have four named regions, such as A, B, C, D, then the average will involve A, B, C, D, and the complement. When I have five, it will involve A, B, C, D, E, and the complement. So the point is that the average is always taking the average for single region entropies. We'll always take all the regions that have names, and there will be an extra additional region which doesn't have a given name, but it's also there treated as a single region. And if you ask me why,
I think we lost Bartek.
Let's maybe wait for him to reconnect.
hi. So I'm very sorry about this, but about this malfunction. But I am back here. Apologies to everybody, and thank you very much for not having left. Can you see my? Oh no, I haven't shared screen yet. Okay. Can you see my screen?
Yes, yeah.
Sorry, and thank you very much for bearing with me. So yeah, so what I was the last point I was explaining is about why do I invoke some additional region when computing, when taking a tally of what are the single regions? And the answer is, well, why would I need to do this? Suppose that I have 3 regions A, B, C, and then together they do not have a vanishing entropy. The fact that they don't have a vanishing entropy together is the statement that if I compute the Ryuta-Kayanagi tells me that the minimal surface, which is homologous to all of them, has non-vanishing area. And so if I start from ABC and I start shrinking and shrinking, then I must come to an obstruction. And that obstruction has an area equal to this SABC. So the idea is take that obstruction, whatever sits on the other side, imagine that, okay, here's a picture of me shrinking this this curve until I come to a red obstruction. But now suppose that well, okay, so what do I do when I encounter this obstruction? I imagine that there is some additional region on the other side of the obstruction, and this is the minimal surface that separates that region from my region. This fourth region is what I called O. This is the additional region stipulated in the problem. And so that's the reason why why I always need to include an additional region in these in this tally. Okay, so in this talk I will be the object of this talk is to study average entropies that involve the same number of regions, and I will call these average entropies S1, S2, S3, and so on with the superscript. So what's S1? It's the average of, let's say that I have A, B, C, D, E, 5 named regions. Then the average S1 is the average of SA, SB, SC, SD, SE, and the additional 6th purifier region. How about S2? Well, I take all possible doubles here, but after I haven't, but all possible doubles include the doubles that have the purifier, that have the additional region. And by design, those purifier, the regions that include the purifier, are equivalent, have the same entropies as the entropies for all the remaining things. So AO has the same entropy as BCDE. BO has the same entropy as ACDE. Basically, complementary sets of things, including the O, complementary sets of things always have equal entropy. So, so that tells you that the different averages that we will be talking about, they have to range from 1 all the way up to n+1/2. Because I have a single region average, I have a double region average, I have a triple region average. But by the time I get to n+1/2, where n is the number of ranged regions, I can't go any higher because each of these regions have the same entropies as the complements. So it only makes sense to go up to half the regions, which is n+1/2. Any questions about that? So this is the basic thing that we will be studying. Okay. Now you can ask, so the next step is to ask, what do we know about these average entropies? And here's a little sheet that describes one fact we know about them, which is that let me start from this first statement we studied on one of these one of the earlier slides, which is subadditivity. A plus B is greater than or equal to AB. And then what I'm going to do is to take a full orbit of the permutation group on this inequality. So that will include A plus C greater than AC and B and C greater than BC and so on. This is an orbit of permutations applied to A, B, C, and O. And these are all true inequalities, and I'm going to add them up. And after I add them up, all terms that are here, obviously, since I've added the full permutation group, every term in the resulting sum is going to be some combination or some multiple of the averages, of the average 1 region entropy, of the average 2 region entropies, and so on. And in fact, those averages are going to come with exactly the same coefficients as they did in the original inequality. So I had 2 terms which involved a single region, and I have 2s1. I have 1 term which involves a double region, and I have an s2. And so the statement is that you take any inequality, and every time you see a single region or a region which includes everything except 1, then you replace it with s1. Every time you see a double region or a complement of a double region, you replace it with s2, and so on. This is a very simple substitution. And every inequality that was previously known before, that was, for instance, from this intimidating sheet I showed you listing all inequalities, each one of them automatically gives me some statements about averages simply by that very trivial substitution. So let's do this substitution to the inequalities. Let's apply it to the inequalities that we have seen before. And the answer is this one. Subadditivity gives me this. Monogamy of mutual information, which was one of those inequalities, gives me this. Now, all of these three complicated ones marked in red, this one, and this one, the three red complicated ones, give me this thing, which is very simple in the end. And then I have the others marked in purple, but the others marked in purple turn out to, this is what happens when I average over, or when I sum over permutation orbits of these inequalities. But these others turn out to imply something that is strictly weaker than these three. And so we're going to forget about the weaker stuff. So at the end, the inequalities that we got after this symmetrization procedure, so after going to the language of, to the context of averages, is that we just got three inequalities here. But if we're talking about regions A, B, C, D, E, in total, we have n+1/2, which is three different options. So we have three inequalities in a three-dimensional space, which is spanned by S1, S2, and S3. Hopefully you will agree with me that this is remarkable because we have the smallest possible number of inequalities we could have had. Our playground is three-dimensional, S1, S2, S3, and we have three inequalities only. So I have drawn them for you, what they do for you. This is S1, this is S2, and this is the S3 axis. And I've drawn what these inequalities do in terms of carving out an allowed region of entropies. And hopefully you will see that they cut out a cone. This cone is called the cone of average entropies, or the holographic cone of average entropies. And the remarkable thing about this cone is that it is simplicial. In other words, I'm in a three-dimensional space and I only have three binding planes for this cone. These three binding planes are these three inequalities. Yes. Now, there was nothing a priori that guaranteed that there should be only three inequalities here. I could have been talking about, I would always be talking about a cone in a three-dimensional space, but maybe there will be 20 different inequalities, which would bound some much more complicated cone. That turned out not to be the case. There are only three. So three binding planes in a three-dimensional space means that this is a simplicial cone. Its cross-section is a simplex. And this is the simplest possible answer that we could have had, that we could have possibly obtained to this question of what averages of entropies are allowed by the geometry. Okay, so the statement that I just made, which is here's a cone of what's allowed at the level of 5 named regions, A, B, C, D, E. I redrew the cone for you here as a cartoon. Okay, I just told you that this is the answer turned out to be the simplest it could be because the cone is simplicial. It is bound by the minimal conceivable number of hyperplanes which are necessary to actually bind the cone. Okay, so this talk is about, my task in this talk is to introduce a conjecture about this, the cone of average entropies. A conjecture which is supposed to be to apply to any number of regions. So this analysis was only done for when I have up to 5 named regions, A, B, C, D, E. But what if I had 100 named regions or 1,000,000 named regions or an arbitrary number? The first statement I want to make is that this cone will always be a simplicial cone. So it will always have a minimal conceivable number of hyperplanes that bind it. The true physical statement that I want to tell you is that these extremal rays of the cone are very interesting. So what's an extremal ray? It's a place where it's an arrangement of entropies which is marginally consistent with all inequalities except one. Of course, I can't saturate all inequalities, that only happens at the origin, but I can saturate all inequalities except one, and that's these extremal rays. And the statement is that these extremal rays, in the language of physicists, represent, first of all, stages of thermalization. And in the truly gravitational language, these are the things that actually represent stages of unitary black hole evaporation in the so-called islands program. And so these things we're doing by studying these inequalities, ahead of time, when we started this study, we had no idea that this was going to give us anything interpretable. All we knew was statements of this type, and we were definitely intimidated. But at the end of the day, this analysis reveals that this stuff actually knows about black hole physics. And in particular, these extremal rays represent something very definite about the time evolution of black holes. Okay, now, and on a more technical level, we can ask what are the binding inequalities for these cones? And here I wrote them for you. And hopefully you can see that this is a very simple kind of inequality. So these inequalities were super complicated, right? But at the end, when you talk about averages, they all boil down to statements of this type, which are very simple, with a single parameter, which is p, okay? And then these new inequalities, another thing that's remarkable about them is that they are n independent. In other words, they don't depend on how many regions we have. That's also surprising. When I go back here to the original analysis, I had A, B, C, D, E all over the place. And obviously, if you ask me, well, what are the inequalities if I don't just have regions ranging from A to E? But what if I have an F and a G, A, B, C, D, E, F, G? If I'm allowed to play with more components, what are the inequalities that I could write down that I could prove in a similar fashion? And the answer is not known, but whatever it is, there's going to be lots and lots of far more, even more complicated inequalities in that case. And would you expect that after I symmetrize them, they will all boil down to this? But they do. And so there is a remarkable sense of simplicity after you go to the averages. And I want to say that these inequalities here, these are new. They were not known before. And these new inequalities have an additional job. They unify almost all previously known inequalities, and they bound or they constrain all future undiscovered inequalities. And the way I mean this is the following. If I take that inequality, this is a rewriting of this thing. And if I compare it with monogamy, which is AB, AC, da, 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 and I symmetrize it, I will get this. Well, that's exactly the inequality that I'm advertising. If I take the free inequalities from Cuenca, I will get this. And that's just this set of inequalities. So now, what about the undiscovered inequalities that we don't yet know, but presumably in the future at some point we will discover them? Well, they have no choice, but they're going to boil down to this when we symmetrize them. And so ahead of time, we know the structure of these inequalities even before we have found them. And this is what this final point 6 is about, unifying all previously known inequalities and the future undiscovered ones. Okay, so here's a list of claims, and that's the thing that I want to tell you about this holographic entropy cone. So in the remainder of the talk, I want to explain these 2 points here, 2 and 3, which are about thermalization and black holes. So far, everything I've said was a very combinatorial analysis. It was all about what kinds of surfaces can I draw and how can I recombine them. This was just combinatorics and a little bit of geometry. But now, where is the physics? And so the remainder of the talk is supposed to be about the physics and about how the words thermalization and black holes actually enter the picture here. But before I go there, are there any questions? I'm not seeing any questions, so I'm going to move on. So, okay, so let me tell you some heuristics. So first, let's look at the simplest inequality, which is A plus B greater than or equal to AB. This is subadditivity. And you ask, well, how is the, what kind of, let me draw these minimal surfaces. And let me ask, when is this thing ever not saturated? And the answer is that the only way that I can have this not be saturated is that these two regions, A and B, are exactly neighbors on the boundary of my holographic geometry. And so that they will end up being connected like that. And if that's true, then you see that the non-saturation of this inequality can only happen when these things are very, very close to each other. And then the surface AB cannot go very, very deeply in this geometry. It's only going to get stuck very close to these to the asymptotic boundary. And that's a qualitative description of what goes on, but it's correct. And so you see that at least this inequality has no way of knowing anything about what happens very deeply in the bulk of this ADS gravitational geometry. This inequality only knows about stuff that happens very close to the boundary. Now you look at the other inequalities I told you about, which is this one, and then you increase the P. And as you increase the P, you start talking about regions which combine, collective regions, which combine P individual regions at a time, or P minus one or P plus one of them. And the more regions you include, this minimal surface will be reaching deeper and deeper into the bulk. And so these inequalities, if I treat them as if I ask what is the meaning of the parameter P, the idea is that the parameter P allows these inequalities, or the minimal surface which they describe, to reach deeper and deeper into the bulk of the geometry. Now, this idea of going, or this process of going deeper, probing the gravitational geometry deeper and deeper in, is called Holographic Renormalization Group, for those who care about this name. But at the completely pedestrian level, what we're really doing is studying the question of what it means to fall inside a spacetime. And if there is a black hole in the center, then we will be falling towards that black hole. And as we are falling, we are probing the gravitational physics, which is captured by these inequalities with increasing and increasing P. So you can basically think of this P heuristically as a proxy for what happens when you are falling towards some object, such as a black hole. And so that's the most heuristic way of understanding what these inequalities are actually describing. They're describing the regions of spacetime that you're visiting when you fall. Okay, here's a heuristic tool, which is about holographic error correction. So I don't have I think I'm going to mostly skip this slide, but let me just tell you that this region that's deep in the bulk of ADS is known to has a remarkable property, which is that if you want to decode it using the boundary language, the CFT language, then it has, like in this example, it has the property that you have to use physics both in A and B to discover it, or in B and C, or in C and A, but not any one of them is enough. And so you sort of have to have a majority vote about these three components before you can learn something about this region. In quantum mechanics, this is called quantum error correction. And the idea is that you can, this stuff that lives deep in the bulk of ADS, of a gravitational spacetime, which has a holographic description, to learn about what happens deep, you have to decode a certain error, and how deep you are tells you about what kinds of errors are and are not correctable. And these extremal rays of the cone that I told you about have exactly that property. Namely, if you compare those extremal rays one by one to each other, they will differ precisely in the degree of error correction that they offer. And so this, again, confirms the idea that we're learning something about this radial direction, the direction of falling towards the black hole when you study the inequalities. But this slide is a more rigorous version of the previous one, because it rephrases that in the language of error correction. Okay, and remember what my first slogan from the talk. We're basically learning that gravity is about quantum information here, quantum information theory, and this is a specific manifestation of it. Okay, now but I am sure that you would like to hear the statement about black holes, the rigorous statement about black holes, which I want to make if I still have time. So let me speed up to that. So it is a fact that these minimal surfaces can be studied equivalently well on any discretized version of the geometry. So you can take this geometry and discretize it as a graph, and then this will be a weighted graphs where the different edges of the weighted graph basically correspond to pieces of an area that you would have to have if you wanted to find a minimal area that subtends a certain region. And so the process, so this is a technical lemma that finding these minimal surfaces is equivalent to finding minimal cuts through a weighted graph. Okay, so now in that language, given that, let me rephrase everything in terms of minimal cuts. The claim is that the extremal rays of the cone of average entropy all have a very simple structure, which is that they're represented by this graph. It's a graph that is a star graph where all but one edges have weight 1, and one remaining edge has some other undetermined weight. All of these extremal rays have this simple structure. And what I want to tell you about next is that this simple structure, which describes the extremal rays of the cone of average entropy, is in fact already familiar to gravitational physicists, because this is exactly the structure of an evaporating old black hole. So let me tell you about how this comes about. I think I'm going to mostly, I'm going to mostly skip this part. So here's a fact about black holes. It is a famous problem to ask how the entropy of the microscopic von Neumann entropy of a black hole changes during the process of its formation and evaporation. And a basic tenet of quantum mechanics is that if you start from a pure state and you wait long enough, your state always has to remain pure. So even if a black hole forms, at the end of the day, that black hole, you know that Stephen Hawking told us that black holes evaporate. After the evaporation, I should still be getting a pure state at my hand. And the physicist's apparent inability to explain how exactly that happens is called the black hole information paradox. So in the last 2 years or 3 years, there was a proposed resolution to the black hole information paradox. And the proposed resolution basically says, let me apply this formula, which is the quantum corrected Ryuta-Kayanagi formula, and let me apply it very carefully with one additional subtlety. As a black hole evaporates, every time a particle of radiation leaves a black hole, I'm going to capture it and deposit it someplace else and not on the boundary. So I drew such evaporating particles of black hole radiation as particles that are taken out of the picture. So they're not even on the asymptotic boundary here, but someplace else. And I'm asking, what is the entropy of the boundary? And when you apply this formula, you will find that the variation of entropy as a function of time has the correct behavior. Namely, it starts at 0, but it also ends at 0, which is what we want for unitarity and to evade the black hole information paradox. So how does this happen? We have what we're supposed to minimize is the combination of the area plus what's called the bulk entanglement from this orange homology region. And remember, we're always finding the minimal area. So just like in one of my earlier slides about subadditivity, here too, we have basically two options for what this minimal area might be. One option is the horizon of the black hole, and I marked it here with the green. Or the other option is the empty set. The empty set is also an admissible surface here. And when I have the black hole horizon, the homology region, which is orange, doesn't contain any bulk entanglement because these red lines just kind of bridge above it, but they don't neither begin nor end in the orange region. So in the first option, the green option, the black hole entropy is just the area of the green surface and nothing else. But when I take the empty set, well, the empty set has no area, but the bulk entanglement is non-zero because each one of these red regions now begins in the homology region, because the homology region is the full interior. And so in the end, if you ask me what is the entropy, it's the minimum of these two options, the green circle or the red line. And the punchline is that the minimum of a green circle and the red line is exactly what we need to find when we're looking for the entropy of this region in this graph. And this graph is the graph that represents an extremal ray in the cone of average entropy. And so the left picture is a known picture of what happens when black holes evaporate. The right picture is a picture of extremal rays of this cone of average entropy. And in both cases, they have exactly the same structure, namely the entropy of an appropriate region. Here, the boundary, here, this distinguished region that has a different weight. In both cases, that entropy is computed by exactly the same procedure. Take the smaller of two cuts, either a cut that cuts through lots and lots of Hawking particles, or that's this one, or something that is an area, the green thing. And here too, I have two options, either cut through the red Hawking particles, or make a cut here, which represents the area of a black hole. And so the summary is that these extremal rays of the entropy cone are stages of evaporation of a black hole. So I rushed through this last part, but this is basically the punchline of my talk. And here is another picture that shows this. So maybe I'm going to display this picture in closing, and I think I am ready to stop here and say thank you.